谷川岳です。こんなっちゃった。
Wikipedia article called Short Read Sequence Alignment. There are many, many ways to do alignments. The way is the one I've used here, but there are many, many others. So really you want to choose a specific liner appropriate to your biological question. This is a cartoon of the exact type of data I just showed you. So the human genome reference being here along the top. Here's chromosome 1, chromosome 5, here all the sequencing reads. And here are the types of genome variation we want to find using bioinformatics. Point mutations, reference, an indel, insertion or deletion of a base, multiple bases in a small region. Missing DNA, so tumor suppressors in regions that don't have DNA whatsoever. If you don't put DNA into your sequencing device, you're not going to get reads out. That region is not represented. That looks like a deletion. A hemizygous deletion, so one of the two chromosomes is deleted. That means you get half as much data as you extend. A couple different gains, so the cells of genes get amplified tens or hundreds of times. As a result, you get tens or hundreds of DNA sequencing reads happening to that region. And translocation breakpoint, where you take one piece of one gene, attach it to another piece of another gene, and this now has brought one gene on chromosome 5 under regulation, under the control of regulatory machinery that are meant for gene on chromosome 1. So these are very powerful oncogenic trackers in cancer. I'm not going to talk too much about pathogenic sequences, but really not everything aligns to the human genome sequence, especially in cancers like cervical cancer, for example, that where they're one of the original drivers of those cancers is exposure to HPV, ECV, etc.
景色が取れてるといいですけど。
Sequencing reads, and you can align those to other references beyond the human genome. And here's sort of a cheat sheet of sort of the ways that we can think about it in sequence DNA and start to infer the presence of proteins that DNA is wrapped around. Whole genome sequencing, this is put all the DNA into the sequencing or into the sequencing device and sequence whole genome sequencing.
注意注意、ここが危ないんだね。この間も転んだのがこういうところ。安全なところほど危ないという。よそ見するから危ないんですよ。安全なところ。注意注意。
Very high throughput, very inexpensive, the least comprehensive test, but certainly the most clinically actionable. And epigenome modifications, really looking at methylated promoters or other regulatory regions. RNA sequencing, looking at the sort of the functional output of DNA, looking at transcriptome sequencing, either looking at whole RNA sequencing. Targeted RNA sequencing is also a protocol that's being increasingly used in clinical and microRNA sequencing, looking specifically at small microRNAs.
100万人ぐらい登ってますかね、ここ。100万人延べ。100人に1人がいいですね。
I'm not really going to talk at all about protein mapping or DNA fingerprint mapping. That would just be an entire bioinformatics workshop on this topic. I want to show you real data as often as possible. So here's
まあ谷川岳は危険って言われますけど、夏はそうでも、夏はそれほどでもない。冬は。
So here's the region, 9 kb regions, so we're zoomed out quite a bit further than we were on the previous slide. Here's KRAS down here on the bottom, so exon 1 down at this end, the minus strand going from right to left. Whole genome sequencing, you just get a sea of reads, so all those gray sequencing reads I showed you earlier, each got just a little tick on this display because we're zoomed so far out. Exome sequencing, we've essentially used a reagent that will allow us only to focus our sequencing on the exons of interest. Where coding mutations live, this really is much more cost effective. You don't have to look at the regions that you may be interested in if your question is specifically around coding. And RNA sequencing, you let the cell do the exonic selection for you. So in this case, the cell splice out the intron, so all of your reads are only mapped to exons as they should be. You also get the added information of what exons are attached to which exons, and this is also quantitative, so you have very, very high coverage of specific genes. So those genes are expressed at a higher level. The genes that have low coverage are expressed at a low level. I use the phrase whole exome and whole genome sequencing. That's really a bit of a misnomer. They really don't actually measure anything, or probably more specifically, we don't have great bioinformatic methods to assign every single sequencing read uniquely to a region of the human genome. This is actually a slide from my own work in neuroblastoma. In this case, this little tiny slice here is a neuroblastoma tumor. And the y-axis here is a single exon. Each little slice going this way is an exon. One means that we are completely confident in where those reads were aligned and our ability to find mutations in those exons. And so these are the regions where we had no doubt we can find mutations. We have good coverage, so we're well powered. As you get towards the bottom of this plot, you can see our confidence in finding mutations essentially drops to zero. Not just in the exome sequences, which are in these purple, but also in the whole genome sequences as well. This is really sort of a blind spot in the genome where they're highly repetitive, our reads are short, we just cannot be confident that our reads in our ability to find mutations in this region. The other interesting technical aspect is that the blind spots in the genome are often, down here they're essentially the same as exome sequencing, but often they're actually not exactly the same as exome sequencing. This is due to differences in read length, mappability, and with exome sequencing, since you are able to focus the capacity of your DNA sequencer on a relatively smaller genomic footprint, you can sequence those regions to much deeper coverage and might have much greater confidence in the mutation calls at each of those bases. So I still use the terms whole genome and whole exome sequencing because the concept is you are really trying to be as comprehensive as possible, but it does not necessarily mean 100% of the genome or exome sequences.
On the whole exome, what would you say percentage of exome
So at the time it was about 80%, so the whole exome was covered at, I think in this case it was only 14 exons needed to be covered. I think that number has probably gone up to 90 plus now. But I think there's still a lot of room for a lot of sort of custom panels to look, especially at these hard to read regions, and to complement not just Illumina sequencing with other sequencing technologies, longer read sequencing technologies that basically generate much larger reads that are much easier to map across these hard to capture and sequence regions.
You mentioned earlier that you also talked about, and so
I have one slide on PacBio. I'm not going to cover those technologies in great depth actually in this talk. Yeah, rarely. I don't really know of any clinical labs who are currently using those technologies due to problems specifically with background error rate. So in clinical labs especially, we're quite focused on point mutation detection, and those technologies have very high background point mutation error rate. I think they are going to find a place at some point of resolving large structural variation, but they really need to compete on not just sequence quality, but also cost as well. Certainly dollar per base is very hard today to beat Illumina. So that's the data that's by far the most ubiquitous. I wanted to give some context to what RNA sequencing data looks like. This is actually a plot I like to make for all of our RNA sequencing data sets. So for a single patient, I like to just plot all of the exons and just say what is the expression level for all those exons, just to sort of get a feel for what's the dynamic range of our data. I actually do this for almost every data set I get. Before I really do anything, I make a distribution. I look at what is the the shape of the data. And I show it in this case because this is actually data from a breast cancer patient, and we want to know what type of breast cancer are they? Are they ER positive? Are they PR positive? What specific markers are they expressing, and at what level? And what we wanted to do is take the single patient, really just compare it to two reference sets: the tumor from ER positive breast cancer, ER negative breast cancer. The colors are really not showing up great here. In this case, here's the ER right here in red. Here's the ER transcript, and you can see the corresponding transcripts down here in the ER negative breast cancer are really quite low. They're really well below the threshold here. And the patient as well, basically what we want to do is look at, you can't even see it, the story here, we essentially want to take these reference genes, look at their level in the patient, and look at basically compare those reference sets as well. So these dots are higher up in the patient and correspond to a specific threshold in a training set, ER positive cancer, ER negative. The third type of genome variation,
このカメラの入れてるウエストポーチをこれ首にかけて、もう一つの二つの袋があって一つに IC レコーダーして、こういう風になっていて、ラジオはちょっと届きませんね、電波が。
Here's the exact same type of data, the exact same assay run on endometrial carcinoma, and you can see the promoter actually turn completely red. So what's been done in this experiment is they've taken the DNA, they've treated it with bisulfite, and that converts all of the unprotected C's into a T. So this is into a T, and this is really indicative of basically a promoter with a whole series of C's in the CPG arm that are unmethylated, and therefore results in normal expression, normal tissue, but silencing of this gene in cancer. Just like mutation calling, this assay is completely quantitative as well. So you can see this promoter is methylated in this tumor, but you can actually see a sort of a shadow of blue signal as well. And this is still persistent from normal cells present in the same tumor tissue. This is a cheat sheet, great for sort of exams, sort of coming up with the experimental design. But really, none of these assays really stand completely alone. Genome sequencing is great for mutations, copy number alterations, etc. But really, not just read out these sorts of cancer genome variation in one shot.
こういうゲノム、この間、ブックオフにダニのゲノムのあれがあったので、カエルの遺伝子とかちょっと調べるのがいいかも。草の遺伝、植物の DNA とか、カエルの DNA とか、サンプルを持って帰っていいかもしれないですね。ダニのジャーナルで気づきました。発表しましたけど。
Genome variation that can result in loss of gene expression, but you're completely blind to using exome sequencing. So I'm going to go through this list sort of one by one. So the next sort of series of the talk is really just marching through what are these basic cancer genome variation and what do they look like at the read level and how do we detect them and think about them. So I'm going to start with somatic mutations, sort of the most famous type of mutation, single base pair change. I want to start again with what does genome variation look like in normal cells. So in this case, here's a sequencing read stack. I put the reference down here on the bottom, and I've shown here a difference. So in this case, half the reads at this exact position have a C, and half the reads have a T. T being the one that doesn't match the reference. In this case, this is a heterozygous variant. So I showed you those chromosomes at the beginning. You have two copies of every gene. In this case, one gene has a C, one gene has a T, and next-gen sequencing is highly quantitative. You can literally count the number of C's, count the number of T's, and get more or less a 50-50 balance. In cancer, specifically in applied or clinical genomics, this is confounded by a few features of the tissue that we're actually given to work with. The first one being that the tumor tissue often yields variable DNA quality and quantity from tissues that are used in routine diagnosis. So in cancer, certainly in cancer diagnosis,
帰ってまた靴洗わないとな。 NASA の青がいいですね。北国屋の帽子もやってます。
sort of 50 base pairs at the low end, the 300 at the high end. So even these small fragments are still useful for DNA sequencing, but there is this additional challenge of just making this DNA sequenceable or compatible with the Illumina sequencers.
足の神経が戻ってきたんだけど、1週間休むとちょっとだけ治ってくる。
Tumor cells and invading or surrounding normal cells. So this is actually a screenshot from a laser capture microdissection experiment.
仕事が悪いですね。もう下の方だけの雪。
Circled all the tumor deposits, and in this case, to enrich the number of cancer cells for analysis, we use the laser to cut out these cells and capture those, and then do DNA extraction from purified cells.
とはいえ1時間っていうのは本当ですか。
Secondary approaches where we'll just put all of this DNA together and sequence this actually to great depth instead. So instead of just generating 15 reads like I showed in that germline example, we'll generate 150 or 1,500 or 15,000 just sequence normal in the search for somatic mutations in highly pure tumors. So you may hear this concept of contaminating stromal cells referred to as tumor purity or also tumor content. So the two buzzwords that you'll see to describe this idea of tumors being a mixture of cancer cells and non-cancer cells. The other challenge I touched on earlier is tumors can have multiple copies of chromosomes. So that assumption of 2 copies of every gene is broken in cancer, and even more confounding, not every chromosome is necessarily at the same copy state. So one here is at 4 copies, also 2 is at 3 copies. It'll actually be easier to find mutations potentially in the 3 copy chromosome. So you may hear this concept referred to as aneuploidy or diploidy. One way around this is to sequence the DNA from these admixed to death. This is really where sequencing still really has a home. This is the same sample sequence 2 ways, genome sequencing and exome sequencing. In this case, this genome has only 15 reads. The exome has nearly 140. Really gave the algorithm or the alignment the power to test mutations that actually, or the DNA fragments that correspond to the reads supporting this actually this actionable mutation. So really trying to think about what is the goal of the programmatic analysis.
ご飯を食べたら、ちょっとじゃ電話のあれかもしれない。電波塔が出てきそう。
Low coverage regions, especially in highly aneuploid or low purity tumors, mutations may be missed. One benefit of the sequencing approach is the ability to infer tumor purity and potentially subclonal structure as well. If you have the depth to detect these very rare variants, this is one algorithm. The way to read this plot here, the chromosomes ordered left to right. Each dot here is a variant, a germline variant.
2時間ぐらいですか。2時間半。
Never changes as you get these shifts in both allele coverage, but also allele specific coverage, but also coverage from the whole genome itself. The goal being to generate these genome-wide copy number alteration plots, where you should have 1 copy of red allele, 1 copy of blue allele. So normal cells just have 2 blue and red lines, just line up nicely along this baseline. In this case, this is a highly aneuploid tumor. Lots of copy number gains, lots of deletions. Actually, this chromosome here is quite interesting, where one allele is just deleted. It's basically a copy 0. And to stay alive, the cell actually duplicated the other chromosome. So it still has 2 chromosomes. They're just both the same. These algorithms can infer both tumor content and average ploidy. They can infer from knowledge that normal cells can produce DNA as well. So you're not necessarily expecting perfect 50-50 balances between mutant and non mutant allele, you actually get this sort of dilution effect of having normal self-information. And then tools like high-clone
三角
file
点っていうんですか、これ。
that will take this type of data, they'll take your somatic mutations, and then basically answer the question or give you a readout into what percentage of the cancer cells have these mutations. So in this case, all of these mutations here are all in 100% of the cells. These mutations here are in roughly 80% of the cells. And here are subclone mutations that are often visible to shallow whole genome sequencing that are in this case only visible in 20% of cells. So something that you can see with deeper profiling and you can assign to a specific subclone. In this case, very important mutation present in the clonal cancer population. As Francis alluded to, Illumina sequencing isn't the be-all and end-all of DNA sequencing in the world. I've just shown an example here where we use long-read PacBio sequencing to complement what we have with Illumina sequencing. So in this case, we've discovered mutations in these two genes here. We wanted to confirm that those mutations were real. So in this case, this is a point mutation, so the base changed colors, so you can see it. This was a out-of-frame 2-base deletion. And we wanted to ask the question, can we see those in PacBio data as well? The real challenge with this technology, at least at the time, is a little old now. You can see the real variant shining through, but you can see this background error noise. What's useful is the background errors are not necessarily always in the same place, but they're certainly there, so you also have this background effect that can make variant discovery sort of more challenging than it would be in that cleaner Illumina data. Certainly not really a problem with point mutations, because the reads that have the variants are very clear. This we thought might be more of a challenge in the indel space, because the types of errors that the PacBio sequencer makes were specifically insertions and deletions. But you can see this variant was very highly recurrent, so something that we could call out on both platforms. This is where it's very useful, especially if you're looking for challenging types of cancer genome variation, to have an orthogonal technology to validate what was discovered on one platform with something
最後、怪我しないように。
I want to talk a little bit about depth. Why sequence deeper? In addition to overcoming the challenges of purity and fluidity, the ability to really detect very, very rare sequencing variants. That's from the plot of how low can you go in terms of allele fraction and with depth. We actually published this last year in a ctDNA study. Exome sequencing is sort of being in this realm of 100 to 200x coverage. The clinical lab will sequence our panels to 500x plus. If you really want to get serious about subclonality, we'll use highly targeted custom assays to look for these very rare subclones. Certainly in tumor DNA, we're currently sequencing those to 25,000x coverage. In this case, this is DNA from tumors that have been eaten into the bloodstream, so we have to sequence past all the contaminating normal DNA fragments and find the 5, 10, 15 fragments of DNA that are derived from tumors. You can't necessarily. So we will often, certainly in that study, we had the tumor, we had a bone marrow aspirate in the case of multiple myeloma, which I'll just jump here. So we knew what the answer key was, we knew where the somatic mutations were.